hopefully the last few people get here shortly. We're gonna go ahead and get started. So good morning, everybody. I hope your week's been going well so far, and that you had a great weekend. All those fun things. Today and tomorrow is gonna be a lot of notes. Next week, we're gonna do practice problems with some of the new content we're gonna take notes on today and tomorrow. So I do apologize in advance. It's gonna be pretty dry, and it's going to feel like a lot of information. So I do recommend that you have something to write with, take some notes. And yeah, it's going to be a lot of me talking right now. First, we're going to start by polishing off the last little bit of section 9.3 that we did not get to last week. And then we'll do the notes for section 10.1. And we'll get into what that is when we get there. All right, so I'm going to share my screen here. We're going to go over the last few slides that were in the Desmos activity. I'm not going to need you guys to join the activity because it's just notes. There's no part of the activity for you to participate in. It's just some notes and things. So we're going to do that first, and then we'll get into section 10.1. And as usual, if you do have any questions, comments, concerns as we go over these things, raise your hand, shout at me. Otherwise, let me know, and I'd be happy to pause and explain things in more detail. All right, so here we go, where we kind of left off last week. If you remember, we did the example having to do with a two-sided test, and we're now connecting that two-sided test to the confidence intervals. Remember, 9.3 was significance tests about means. There is a strong connection between two-sided tests and confidence intervals that is far stronger than the connection between those things with proportions. This is because both inference methods for means use the standard error of the sample mean in the calculations. If we're looking at the test statistic and the confidence interval calculation, they both use the sample standard deviation divided by the square root of the sample size in their calculation. This S sub x divided by square root of n. Since they're both using a same factor, it ties them together very well. And so we have these extra little notes here. A two-sided test at significance level alpha, suppose alpha is 0.05, and a 100 times 1 minus alpha % confidence interval, which would then correlate to a 95% confidence interval if alpha is 0.05, give similar information about the population parameter. Okay. When the two-sided significance test at level alpha rejects the null hypothesis, the 100 times 1 minus alpha % confidence interval for mu will not contain the hypothesized value mu sub 0. Right, so essentially, the confidence interval will not have the hypothesized value. So if we reject the null hypothesis at the significance level of alpha equaling 0.05, that means that if we constructed the confidence interval at a 95% confidence level, mu sub 0 would not be in that confidence interval. When the two-sided significance test at level alpha fails to reject the null hypothesis, the confidence interval for mu will contain mu sub 0. And so this, on the other side, if we fail to reject the null hypothesis, then that certain value will exist in our confidence interval. And so that's how we have this really specific connection between two-sided tests and confidence intervals. It's not exactly the same correlation between one-sided tests, right? Where we just have a strictly greater than or strictly less than alternative hypothesis. This only has to do with those two-sided tests where our alternative is that it's just not equal to the null. All right. There's some interesting connections there. Now, the other thing we can do with a one sample t-test is do inference for means about paired data. This is different than what we will see in chapter 10. They seem very similar, and we have to be careful about which one we use. Paired data is a a scenario in which like we're comparing things within the same group. right? And so we'll see an example of this here. Comparative studies are more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. Study designs that involve making 2 observations on the same individual or 1 observation on each of 2 similar individuals result in paired data. Right? This sentence here gives us the definition of when it's paired data. Right? If we're making observations about 2 separate groups with different individuals, that becomes what we'll do in the next chapter. Okay. When paired data result from measuring the same quantitative variable twice, as in the job satisfaction study, we can make comparisons by analyzing the differences in each pair. If the conditions for inference are met, we can use one sample t procedures to perform inference about the mean difference, mu sub d. These methods are sometimes called paired t procedures. And so when we have paired data, we find out their difference, and then we essentially treat the difference as our sample set of data. And so to help with this, we have a short video, which the volume should work. If you guys can't hear this video, please let me know.
Hi, this is Jason Molesky. Let's take a look at paired data and one sample t procedures. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. Now, during one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took caffeine and the placebo was randomized, and at the end of each 2-day period, a test for depression was given to all 11 subjects. Now, researchers wanted to know if being deprived of caffeine would lead to an increase in depression. Now, this table contains data on the subject scores on a depression test. Higher scores show more symptoms of depression. So we have our 11 subjects here and their depression scores on the first test. We also have our 11 subjects and their depression scores on the placebo test. And then we also have the difference between those scores. And we went placebo minus caffeine because for the most part, the placebo scores are greater than the caffeine scores, and that resulted in positive values for the most part in the difference column.
And that's pretty common to do, to try to set it up so that your subtraction results in a positive number most of the time. Right? If these numbers were backwards, like say the caffeine had a higher score than the placebo, you would switch the order of the subtraction so you still have results that were more positive numbers than negative. These positive numbers just are easier to work with.
Now, why did researchers randomly assign the order in which subjects received the placebo and caffeine? Well, researchers want to be able to conclude that any statistically significant change in depression score is due to the treatments themselves and not to some other variable. One obvious concern is the order of the treatments. Let's suppose caffeine were given to all the subjects during the first 2-day period. What if the weather were nicer on these 2 days than during the second 2-day period? Well, the researchers wouldn't be able to tell if a large increase in the mean depression score is due to the difference in weather or due to the treatments. Random assignment of the caffeine and placebo to the 2 time periods in the experiment should help ensure that no other variable is systematically affecting the subject's responses. Now let's carry out a test to investigate the question. If caffeine deprivation has no effect on depression, then we'd expect the actual mean difference in depression scores to be 0. That is, the scores when the subjects were on caffeine would be pretty much the same as the scores as when they were on the placebo, so therefore the difference would be 0. So our null hypothesis is that the mean of the differences is 0, while the alternative hypothesis is that the mean of the differences is greater than 0, where the true mean difference is defined by mu sub d, and we did note that that was placebo minus caffeine. Now, because no significance level is given, let's use alpha equals 0.05. Well, to use a paired t-test, let's first check our conditions. We note that the researchers randomly assigned the treatments placebo, then caffeine, caffeine, then placebo to the subjects, so that condition is met. Since we aren't sampling, it's not necessary to check the 10% condition. And when it comes to the normal large sample condition, we don't know whether the actual distribution of difference in depression scores is normal, so we're going to have to do a little extra work here. With such a small sample size, we need to examine the data to see if it's safe to use t procedures. Well, here's a histogram, a box plot, and a normal probability plot of these 11 differences. The histogram itself does have an irregular shape with so few values. The box plot shows a little bit of right skewness, but no outliers here, and the normal probability plot is slightly curved, indicating there is some slight skewness. However, with no outliers and no strong skewness, the T procedure should be pretty accurate. Now we entered the differences in list 1 and then used the calculator's t-test with the draw command to perform this test. We see our statistic here is 3.53, and we get a p-value of 0.0027. That's the area to the right of t equals 3.53 on the t distribution curve with 10 degrees of freedom. Now, because the p-value is 0.0027, and that's significantly less than 0.05, we reject our null hypothesis. We have convincing evidence that the true mean difference, placebo minus caffeine, in depression score is positive for subjects like these. Now, for some additional practice with paired data and one sample T procedures, try exercise 80.
All right. And so there's a couple things I want to point out within this example. Right now, what's on this screen here with the conclusion, because the participants in the study were not randomly selected, and they were just people who were available, they can only make conclusions about subjects like these, about the type of people who participated. They cannot make conclusions about the larger population. And then also, there is, we'll go here.
And then placebo to the subject, so that condition is met.
The 10% condition, they're not sampling. All right, so it isn't necessary to check the 10% condition. In an experiment, in a study like this, when you're not necessarily sampling without replacement, you don't have to check the 10% condition. Right? If you're randomly selecting, students from a school population, right, and then collecting data about them, about a certain characteristic, right, then you check the 10% condition. When you just have a group of participants in a study, right, and those are just the people who are going to participate, and you're assigning treatments to them, right, in an experiment, you're not sampling. Okay, so then we don't need to check the 10% condition. So there's a couple of things to point out. Are there any other questions about this example? So then we get into using tests wisely, and this comes up over and over again with different things that we look at. So carrying out a significance test is often quite simple, especially if you use a calculator or computer. Using tests wisely is not so simple. Here are some points to keep in mind when using or interpreting significance tests. How large of a sample do you need? A smaller significance level requires stronger evidence to reject the null hypothesis. Right, so the smaller you get with alpha, the stronger evidence that you need. Right? Larger alpha, less evidence, so to say. Higher power gives a better chance of detecting a difference when it really exists. So if we can increase the power, that helps our chances. At any significance level and desired power, detecting a small difference between the null and alternative parameter values requires a larger sample than detecting a large difference. Okay. So essentially, if you're trying to detect something that's relatively small, you need a bigger sample size. If you're trying to detect something that has kind of a larger range of possibilities, and you're trying to find that difference, a smaller sample size will probably suffice. It depends on the study and the setup and everything. And again, sometimes if you're provided the problem is a word problem, you can't change the size of the sample. Right? It is what it is. But if you're designing a study, these are things to consider. Statistical significance and practical importance. When a null hypothesis, no effect or no difference, can be rejected at the usual levels, alpha equaling 0.05 or alpha equaling 0.01, there's good evidence of a difference, but that difference may be very small. When large samples are available, even tiny deviations from the null hypothesis will be significant. And so, are your results, even though they're statistically significant, are they practical? Are they important results, right? And this comes down to what you've decided to study and how you've designed your study. You could find something that shows is statistically significant, but if you're trying to find significance about increasing something's score by like 1%, does that even affect does it have any kind of effect? Even though you found significance, that it has that specific increase, what does that actually mean? Is it practically important? And then beware of multiple analyses. Statistical significance ought to mean that you have found a difference that you were looking for. The reasoning behind statistical significance works well if you decide what difference you are seeking, design a study to search for it, and use a significance test to weigh the evidence you get. In other settings, significance may have little meaning. In other words, if the same thing has been analyzed over and over again and the tests and designs of these studies have been adjusted to make sure they find significance, it's watered down, right? That significance now has very little meaning because essentially the study was targeted to find that result. It wasn't by accident, so say it was purposefully done, and it wasn't like properly designed at that point. All right, is there any other questions about section 9.3? So that means we're gonna stop that part and we're gonna go into chapter 10. So again, if you're taking notes, start a new heading, do whatever you do. We're going into chapter 10 now. Chapter 10 only has 2 sections, 10.1 and 10.2. And chapter 10 combines the things that we have learned essentially starting from chapter 6, 7, 8, and 9. So the previous 4 chapters are all kind of combined into what we do in chapter 10. All right. So it's drawing back on a lot of things that we've covered so far. All right. So here we go. We're in chapter 10, comparing 2 populations or groups. And section 10.1 has to do with comparing 2 proportions. All right, so we'll be dealing with parameter P. All right. Section 10.2 will be comparing 2 means. In this section, we will learn how to describe the shape, center, and spread of the sampling distribution of the difference of 2 sample proportions. All right, that goes back to chapter 7. We will determine whether the conditions are met for doing inference about P1 minus P2. That is chapters 8 and 9, a little bit of chapter 7. We will construct and interpret a confidence interval to compare 2 proportions, chapter 8, and perform a significance test to compare 2 proportions, chapter 9. All right, so the concepts and the tools that we used in those previous chapters will be used in this chapter. There will be some slight variation to the formulas to account for the fact that we're dealing with 2 samples. So suppose we want to compare the proportions of individuals with a certain characteristic in population 1 and population 2. Let's call these parameters of interest P1 and P2. Those are subscript 1, subscript 2. The ideal strategy is to take a separate random sample from each population and to compare the sample proportions with that characteristic. All right, So that is one way in which we will apply what we learned in this chapter when we're comparing characteristics of two different populations. What if we want to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment? This time the parameters P1 and P2 that we want to compare are the true proportions of successful outcomes for each treatment. We use the proportions of success in the two treatment groups to make the comparison. Right? And so then in this case, this is an experiment setting, and we're testing the two different treatments. Right? One could be no treatment, and one could be some new thing that they're testing, like placebo and new drug. Right? What's the percent of effectiveness? This is different than the example we just saw in 9.3 because the two treatments are applied to two separate groups of people. The same person is not receiving the two treatments. Okay. So these are two types of scenarios where we'll be able to use the things we learned in 10.1. And we have some new notation here. So if we have population or treatment 1, the parameter will be P subscript 1, statistic will be P hat subscript 1, and the sample size is N1. Similarly, for population or treatment 2, we get P sub 2, P hat sub 2, N sub 2. The key thing is that you need to identify which variable and value goes with which population or treatment. You can use numbers 1 and 2. You could use letters A and B. You know, it doesn't matter as long as you tell the reader which one goes with which population and be consistent about it. So you will need a moment to write anything down from this screen. So the sampling distribution of a difference between two proportions. To explore the sampling distribution of the difference between two proportions, let's start with two populations having a known proportion of success. So we're comparing two different schools. At school 1, 70% of students did their homework last night, and at school 2, 50% of students did their homework last night. Suppose the counselor at school 1 takes an SRS of 100 students and records a sample proportion that did their homework. School 2's counselor takes an SRS of 200 students and records a sample proportion that did their homework. Notice in this scenario, the sample sizes from each population do not need to be the same. We don't need to take an SRS of 100 from each school. We can do different amounts. Okay. What can we say about the difference P hat 1 minus P hat 2 in the sample proportions? So this is what we're going to explore. Using Fathom software, which is a statistical modeling software that the publishers have that we don't. We generated an SRS of 100 students from school 1 and a separate SRS of 200 students from school 2. The difference in sample proportions was then calculated and plotted. We repeated this process 1,000 times, and that resulted in our sampling distributions of the sample proportions. We get it for school 1, school 2, and the difference, school 1 minus school 2. What do we notice about the shape, center, and spread of the sampling distribution of the differences, P hat 1 minus P hat 2? Well, just like the two sampling distributions that it came from, it's approximately normal, right? The center of school 1's mean sampling distribution of the sample proportions is 0.7, we get 0.5, 0.7 minus 0.5, hey, that's the center of this one, 0.2. That makes sense. The spread, we'll get into how to calculate this shortly. I don't know if you can necessarily see the connection between the three numbers here quite yet. It has to do with the variance. So we'll get there shortly. Again, this is our data. Both P hat 1 and P hat 2 are random variables. The statistic p hat 1 minus p hat 2 is the difference of these two random variables. In chapter 6, we learned that for any two independent random variables, x and y, the mean of x minus y is equal to the mean of x minus the mean of y, and the variance of x minus y is equal to the variance of x plus the variance of y. This allows us to then kind of put this stuff together here. We're going to choose an SRS of size n1 from population 1 with a proportion of success p1 and an independent SRS of size n2 from population 2 with proportion of success p2. So the next part of this is showing the shape, center, and spread of our sampling distribution of the difference between sample proportions. This becomes a great big mouthful of variables and numbers and things, so bear with me. So when n1 p1 and n1 times 1 minus p1, n2 p2, and n2 1 minus p2 are all at least 10, I mean we have at least 10 successes and 10 failures in each sample based on the proportions, the sampling distribution of p hat 1 minus p hat 2 is approximately normal. Right. The mean of the sampling distribution is p1 minus p2. And that goes back to this fact here. Right, because of what we learned in chapter 6 with our random variables, and again then in chapter 7 with our sampling distributions, the mean of the sampling distribution, if we have a good test statistic or a good estimator, should be the same as the population proportion, which is why we get p1 minus p2. And then finally the spread. The standard deviation of the sampling distribution of p hat 1 minus p hat 2 is the square root of p1 times 1 minus p1 divided by n1 plus p2 times 1 minus p2 divided by n2, as long as each sample is no more than 10% of its population, which is our 10% condition. Right? And essentially, the shape is dependent on our large counts condition, as we come to call it later on. All right. Does anyone need a moment to write anything down from this screen? And we have a visual of this information. The curve here is our sampling distribution of p hat 1 minus p hat 2. Horizontal axis represents all the possible values of p hat 1 minus p hat 2 based on our sampling distribution. The standard deviation helps us determine the width of our distribution, and the mean, p1 minus p2, should be the center of our distribution. All right, so suppose, again, we have our same context, right? We have our two large high schools. School 1, 70% of students did their homework. School 2, 50% of students did their homework. We have an SRS of 100 from school 1, an SRS of 200 from school 2. We want to describe the shape, center, and spread of the sampling distribution of p hat 1 minus p hat 2. All right, because the large counts condition is satisfied, right? 70, 30, 100, and 100 are all at least 10. The sampling distribution of p hat 1 minus p hat 2 is approximately normal. We've now described the shape. The mean is p1 minus p2, which is 0.7 minus 0.5, and we get 0.2. Now we have the center. The standard deviation is the square root of 0.7 times 0.3 divided by 100 plus 0.5 times 0.5 divided by 200, which is equal to 0.058. And we now have the standard deviation, and we have completely described the shape, center, and spread of our sampling distribution. Is there anything I can clarify here? Are there any questions? So next we'll talk about confidence intervals. So essentially now we're moving on to chapter 8. All right, when data come from two random samples or two groups of randomized experiment, in a randomized experiment. The statistic p hat 1 minus p hat 2 is our best guess for the value of p1 minus p2. Remember in chapters 8 and 9, when we're doing confidence intervals and significance tests, we do not know the value of the parameter. When we're doing a sampling distribution, we typically are given the value of the parameter. In these new cases, confidence interval significance, we don't know. So we're estimating. Right, so we can use our familiar formula to calculate a confidence interval for P1 minus P2. We get statistic plus or minus critical value times the standard deviation of statistic. Right, when the 10% condition is met, the standard deviation of the statistic, P hat 1 minus P hat 2, is the square root of P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2. If the normal condition is met, we find the critical value Z star for the given confidence level from the standard normal curve. The normal condition is otherwise known as that large counts condition. And we have at least 10 successes and 10 failures in each sample. All right. But again, there will be some caveats here. Does anyone need a moment on this screen to write anything down? All right, and so then we have our conditions for constructing a confidence interval about a difference in proportions. It's the same three conditions that we've seen previously. However, we now must check these three conditions for each of our populations and samples. All right, so random, the data come from two independent random samples or from two groups in a randomized experiment. 10% condition when sampling, again, without replacement. So if we're not sampling without replacement, we don't need to check this, but there it is. Check that there's at least that the sample size from population 1 is less than 10% of population 1, and the sample size from sample 2, population 2 is less than 10% of population 2. And we have our large counts rules. The counts of successes and failures in each sample or group are at least 10. Because we don't know the values of parameters P1 and P2, we replace them in the standard deviation formula with the sample proportions. The result is the standard error of the statistic P hat 1 minus P hat 2. And we get the square root of P hat 1 times 1 minus P hat 1 divided by N1 plus P hat 2 times 1 minus P hat 2 divided by N2. That is our standard error. Would anyone like a moment to write anything down from this screen? I'm back, yay. Can you guys hear me? My connection just dropped for a minute.
Yes, we can hear you.
Awesome, okay, just double checking. All right. All right, so let's go on. All right, so then we get our two sample Z interval for a difference between two proportions. This would be our inference method for the difference between two proportions, right? One of the inference methods. So when the conditions are met, an approximate C% confidence interval for P hat 1 minus P hat 2 is the difference between those proportions, P hat 1 minus P hat 2 plus or minus Z star times the standard error, square root of P hat 1 times 1 minus P hat 1 divided by N1 plus P hat 2 times 1 minus P hat 2 divided by N2, where Z star is the critical value for the standard normal curve with C% of its area between negative Z star and Z star. And we find this Z star the same way that we did in chapter 8, right? We must use table A, right? And it depends on the confidence level that we're interested in. If we're at a 90% confidence level, right? Then the 90% confidence level leaves us 10% 10% between each tail leaves us 5% for each tail, right? So then we find the z value corresponding to the proportion of the tails. We'll see examples of this next week when you do this again, if you're not remembering this, and that's okay. Does anyone need a moment to write this down? That leads us to our significance test for P1 minus P2, Chapter 9. An observed difference between two sample proportions can reflect an actual difference in the parameters, or it may just be due to chance variation in random sampling or random assignment. Significance tests help us decide which explanation makes more sense. The null hypothesis has the general form, H not such that P1 minus P2 equals the hypothesized value. We'll restrict ourselves to situations in which the hypothesized difference is 0, meaning there's no difference. Right? Then the null hypothesis says that there is no difference between the two parameters. And we get that we can write this as H naught such that P1 minus P2 equals 0, or H naught such that P1 equals P2. They're essentially the same. The alternative hypothesis says what kind of difference we expect. Either that the difference is greater than 0, the difference is less than 0, or that the difference is just not 0. It might be greater than, it might be less than. That results in the two-sided alternative. Right, so essentially it's the same set of possibilities that we had for significance test for one sample, right? That we saw in Chapter 9, except now we have the two parameters, and we're using that difference. We're doing subtraction. Does anyone need a moment to write anything down from this screen? Or does anyone have any questions and need clarification? And again, we have the same set of conditions for performing a significance test about a difference in proportions, which is the same set of conditions for constructing a confidence interval, the random, 10%, and large counts condition. They're exactly the same. So then to do a test, we need to standardize p hat 1 minus p hat 2 to get a z statistic. And again, we get test statistic equals statistic minus parameter divided by the standard deviation of the statistic. So we get z equals p hat 1 minus p hat 2 minus 0, because our parameter is that the difference is 0, and divided by the standard deviation of the statistic. If the null hypothesis is true, the two parameters are the same. We call their common value p. We need a way to estimate p, so it makes sense to combine the data from the two samples. This pooled or combined sample proportion is p hat sub c. This is the count of successes in both samples combined, divided by the count of individuals in both samples combined. All right. We get x1 plus x2 divided by n1 plus n2. And this is a pooled sample proportion. We need this to construct to perform our test, to get our z statistic. And so now we have our two sample z test for the difference between two proportions. This is the inference method for our significance test. And we suppose the conditions are met. To test the hypothesis, h not such that p1 minus p2 equals 0, first find the pooled proportion p hat c of successes in both samples combined. Then compute the z statistic. Z is equal to p hat 1 minus p hat 2 minus 0, divided by essentially the standard deviation of the statistic, where the statistic is p hat sub c. We have the square root of p hat sub c times 1 minus p hat sub c divided by n1 plus p hat sub c times 1 minus p hat sub c divided by n2. So the numerator in both of these is the same value. We then find the p-value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis h sub a. If the alternative is that it is greater than 0, we find the proportion under the curve greater than that z value. If we are less than 0, then we find the proportion to the left of that z value. And if we are two-sided, we find the proportion greater than the positive z value or less than the negative z value, and then we multiply it by 2 to get the whole thing. Would anyone like a moment to write anything down? All right. Many important statistical results come from randomized comparative experiments. Defining the parameters in experimental settings is more challenging. Most experiments on people use recruited volunteers as subjects. Right. When subjects are not randomly selected, researchers cannot generalize the results of an experiment to some larger populations of interest. Research can draw cause and effect conclusions that apply to people like those who took part in the experiment. Unless the experimental units are randomly selected, we don't need to check the 10% condition when performing inference about an experiment. So there are cases when we're dealing with experiments when we do not need to check the 10% condition. We only need to check the random, meaning there was a random assignment of the treatments, and the large counts condition. Is there anything I can clarify? Are there any questions about this stuff from 10.1 here? And that brings us to the end of the presentation. Those are the notes for section 10.1. All right, so again, as I said, that's just the notes. It's a lot of information. It's a lot of new notation and formulas, and it might look like gobbledygook right now, and that's okay. Tomorrow we will look at the notes for section 10.2. And then next week we will see examples and do practice problems in class to help make this make more sense. I do want to point out that in our class in Canvas, if we go to our modules, minimize these guys. I have the foundation for chapter 10 set up. We have our notes and resources ready for both sections. I do not have the practice problems and solutions ready yet. I'm working on those. They should be ready by the end of the week. I do have my study guide here. And we have the PowerPoint that you guys just saw if you need to go back through that. If you haven't looked at the study guides that I put up, it's kind of a boiling down of what's in the textbook into what you want. Like the things that I think you need if it wants to pop up here. We'll see. Maybe not. I'll close that for now. There's a bunch of AP Daily videos. There's some videos that are examples from the textbook, and there's also calculator instructions for confidence interval and significance tests for difference in proportions, and then the textbook. All right, guys, please don't forget that these resources are here. They can be very helpful in letting you see other examples or other ideas from the chapter that maybe didn't make sense when I talked about them. That's possible, right? So keep that all in mind, guys. All right, other than that, if you do have any questions, comments, concerns, or anything else comes up, please let me know. Send me a message, send me an email, otherwise get a hold of me. And I hope you guys have a great rest of your day, and I will see you tomorrow.